Reality might be the greatest illusion of all. What if everything you can see and touch is just a tiny fraction of what truly exists? Behind the curtain of the visible universe, physicists suspect a hidden architecture of invisible forces and dimensions, secret fields that dictate the rules of space, time, and existence itself. This is a journey into that profound darkness, an exploration of 30 theories about the universe's hidden fields. By the end, you will see the cosmos not as a static stage, but as a dynamic, living tapestry woven from forces we are only beginning to name. We will venture from the chaotic quantum foam that might underpin all of spacetime to the radical idea of a cosmic consciousness field that connects everything. What single hidden force do you think shapes our reality the most? The very fabric of space and time might be churning with a restless, invisible energy. This is the concept of quantum foam, the first and perhaps most fundamental of our hidden fields. To understand it, you have to look beyond planets and stars, beyond atoms, to the very smallest possible scales of reality. At a distance of 1/10,000,000th of a trillionth of a trillionth of a trillionth of a centimeter, a realm called the Planck length, the smooth universe we know dissolves. Here, the rules of Einstein's gravity and the rules of the quantum world collide, and their conflict tears the serene stage of spacetime apart. Instead of a calm, empty void, space itself is theorized to become a turbulent sea of froth. Imagine the surface of a carbonated drink, but trillions upon trillions of times smaller, with bubbles of pure energy and miniature wormholes constantly blinking in and out of existence. This quantum foam isn't made of matter, it is the chaotic, bubbling texture of spacetime itself. It suggests that what we perceive as solid and stable is at its heart a frenetic dance of probabilistic events. The ground beneath your feet, the air you breathe, all of it rests upon this seething foundation. This foam could be the primordial canvas upon which all other forces, like gravity and electromagnetism, are painted. If we could peer into this realm, we wouldn't see particles or waves, but a constantly shifting geometry, a reality where cause and effect blur and the very concepts of here and now lose their meaning. It is a reminder that the universe's deepest secrets are not written in the light of distant stars, but in the dark, chaotic whisper of space itself. This chaotic foam hints at the canvas, but what paints the particles upon it? Enter the Higgs field, a hidden ocean of energy that fills every cubic inch of the universe. Unlike the quantum foam's frenzy, the Higgs field is calm and uniform, a kind of cosmic molasses stretching across all of space. Its purpose is deceptively simple: it gives particles their mass. Think of a famous person trying to walk through a crowded party. As they move, people gather around them, shake their hand, slow their progress. In this analogy, the celebrity is a fundamental particle, and the crowd is the Higgs field. The more a particle interacts with this field, the more it gets slowed down, and that resistance is what we experience as mass. A top quark interacts strongly, so it becomes very heavy. A photon, a particle of light, does not interact with the Higgs field at all, which is why it zips through the universe at the ultimate speed limit. For decades, this was just a beautiful theory. Then, in 2012, scientists at the Large Hadron Collider announced they had found something monumental: the Higgs boson. This particle is not the field itself, but rather a ripple in the field, like a splash in that cosmic molasses. Its detection was the smoking gun, the proof that this hidden field was real. Yet, its discovery solved one mystery while deepening others. The Higgs boson is surprisingly light, and physicists struggle to explain why its mass isn't driven to an astronomically high value by quantum fluctuations. Some whisper it might be protected by a principle of supersymmetry, or that it could be a composite particle made of even smaller things. Even more intriguing is a potential link to the universe's greatest puzzle: dark energy. The Higgs field has a certain energy value everywhere in space, and that energy contributes to the overall density of the cosmos. Could a subtle connection between the Higgs field and whatever drives the accelerated expansion of the universe exist? The field that gives substance to everything we are might also hold a key to the fate of everything that will be. But if the Higgs field gives particles their weight, what gave the universe its size? To answer that, we must travel to the very first moments of existence, to a phenomenon so violent and rapid it defies all intuition. This is cosmic inflation, and it is driven by the most powerful hidden field ever proposed, the inflaton field. In the standard Big Bang model, the universe begins as a hot, dense point and expands. But this model has problems. It cannot explain why the universe is so uniform in all directions, or why its geometry appears so perfectly flat. Inflation solves this with a breathtaking idea. A fraction of a second after the moment of creation, a new field, the inflaton field, dominated the cosmos. Picture a ball resting at the top of a very flat, very high hill. This position represents a state of incredibly high energy. The inflaton field was stuck in this state, and its immense energy had a bizarre effect on spacetime itself. It caused the fabric of the universe to stretch, not just quickly, but exponentially. In less time than it takes light to cross a single proton, the universe ballooned by a factor of at least 10 to the 26th power. That is a 1 followed by 26 zeros. Every region of space was pulled away from every other region at speeds far greater than light itself, ironing out any wrinkles and flattening the overall geometry. This is not matter moving through space, but space itself being created at a staggering rate. Then, like the ball finally rolling down the hill, the inflaton field decayed. Its tremendous energy was dumped into the universe as a hot soup of particles and radiation, effectively kicking off the traditional Big Bang we learn about. The field then faded into the background, its job complete, leaving behind a smooth, vast and flat cosmos as its eternal signature. We see evidence of this incredible event etched into the oldest light in the universe, the cosmic microwave background. This faint afterglow from the early universe is almost perfectly uniform, with only tiny temperature fluctuations. These fluctuations are believed to be quantum seeds, microscopic ripples from the inflaton field itself that were stretched to cosmic proportions during inflation, eventually becoming the galaxies and clusters we see today. The ultimate proof, however, might still be out there. Such a violent expansion should have shaken spacetime itself, generating primordial gravitational waves, ripples in the fabric of reality. Experiments are searching for the faint imprint of these waves in the cosmic microwave background. Finding them would be like discovering the fossilized footprints of the inflaton field, a direct glimpse into that first unimaginable moment when a hidden force decided the fate of everything. Yet that primordial force of inflation faded, leaving behind a universe whose expansion should be slowing under the relentless pull of gravity. For most of the 20th century, this was the accepted story. Then, in the late 1990s, astronomers made a discovery that shattered that calm narrative. They found the expansion of the cosmos is not slowing down at all. It is speeding up. Something is pushing galaxies apart with ever-increasing force. We call this something dark energy, and it is the dominant component of our universe, making up about 70% of everything. The simplest explanation is a cosmological constant, a fixed energy density woven into the vacuum of space itself, a kind of permanent, unchanging pressure. But what if dark energy is not a constant? What if it is alive, dynamic, and changing? This is the theory of quintessence, named after the elusive fifth element of ancient philosophy. Imagine not a static backdrop, but a shimmering, ethereal field that fills the cosmos, its strength ebbing and flowing over cosmic time. Unlike the inflaton field, which decayed violently, quintessence is a slow rolling field, one whose influence is subtle but persistent. Its defining trait is repulsive gravity. Where normal matter and energy pull things together through gravity, This field generates a kind of negative pressure that pushes space itself apart. Think of the universe as a loaf of raisin bread baking in an oven. The dough is space, the raisins are galaxies. In the standard view, the dough rises at a steady rate. With quintessence, it is as if yeast in the dough suddenly becomes more active, causing the loaf to expand faster and faster, driving the raisins ever farther from each other. The fate of everything hinges on the behavior of this hidden field. If it weakens over time, the acceleration could slow, perhaps even reverse into a catastrophic big crunch. If it strengthens, it could lead to a big rip, where the repulsive force becomes so powerful it tears apart galaxies, then solar systems, and finally the very atoms that compose reality. We have not directly detected this field because, unlike the Higgs field, it does not seem to clump around particles. It is perfectly smooth and uniform, a ghostly presence whose only signature is its effect on the largest scales of the cosmos. Its elusive nature makes it one of the greatest puzzles in physics. Is dark energy the unchanging signature of empty space, or is it a dynamic, evolving entity, a quintessence field whose next move will decide the ultimate destiny of all we see? While quintessence might dictate the fate of cosmic expansion, another hidden field could be the very substance holding galaxies together. We call this mysterious, invisible mass dark matter, and one of the most compelling candidates for its identity arises from a beautiful solution to a deep flaw in our understanding of the forces that bind atoms. This is the story of the axion, a particle so light and ghostly it could be flowing through you right now, born from a field designed to fix a cosmic symmetry. The puzzle is known as the strong CP problem. Inside every proton and neutron, quarks are bound together by the strong nuclear force, governed by a theory called quantum chromodynamics. This theory allows for a certain kind of asymmetry, a parameter that, if it had any significant value, would make the neutron possess a tiny electric dipole moment. It would give the neutron a slight positive charge on one end and a negative charge on the other, like a microscopic bar magnet. This asymmetry is labeled CP for charge and parity. Experiments have searched with incredible precision, and they have found nothing. The neutron symmetry is perfect to an astonishing degree. The problem is, there is no known reason in the standard model of physics for this symmetry to be so perfect. The equations naturally allow for a large asymmetry, yet nature has chosen to set this dial to zero. It is as if a complex machine with 1,000 knobs has one specific knob turned exactly to a perfect round number for no apparent reason. This fine-tuning bothers physicists deeply. In the 1970s, physicists Roberto Pexi and Helen Quinn proposed an elegant fix. They suggested a new, dynamic hidden field, the axion field, that permeates all of space. The key is that this field is not static. It can naturally relax or settle to a state that automatically zeroes out that problematic CP knob. Imagine a ball rolling around in a very wide, shallow bowl. No matter where you start it, it will eventually come to rest at the very bottom, the point of lowest energy. The axion field does exactly this for the universe, rolling until it finds the configuration where the strong force's symmetry is perfectly preserved. The particle associated with this field, the axion, is a ripple in that field. It is predicted to be incredibly light, possibly billions of times lighter than an electron, and to interact with ordinary matter only extremely weakly. This makes it nearly invisible, passing through planets and people as if they were not there, and that is where the connection to dark matter becomes electrifying. In the early, hot universe, as the axion field settled to its lowest energy state, it would have begun to oscillate. These universe-wide oscillations are not sound waves, but waves in the field itself. The energy stored in these oscillations, according to the theory, would not have decayed away. Instead, it would have frozen out as a vast, cold sea of axions permeating every galaxy. This C would have exactly the right properties to be the dark matter that governs the rotation of galaxies and bends the light from distant stars. The hunt for these ghostly particles is now a major frontier. Experiments like a DMX, the axion dark matter E experiment, use powerful magnets and ultra-sensitive detectors inside cryogenically cooled chambers to try and convert a passing axion into a faint microwave photon. It is like trying to hear the softest possible whisper in the middle of a hurricane. Other approaches look for axions streaming from the sun, or for their subtle influence on the polarization of light from distant neutron stars. If found, the axion would be a monumental discovery, a 2-for-1 solution that fixes a fundamental flaw in our laws of physics and simultaneously reveals the identity of the universe's most abundant unseen material. It would show that a hidden field born from a need for cosmic symmetry became the invisible scaffolding for every structure we see. The axion field offers a beautiful symmetry, but what if the dark energy field possesses a stranger kind of intelligence, one that allows it to hide in plain sight? This brings us to the chameleon field, a theory born from a desire to solve a major embarrassment in cosmology. If dark energy is a universal field, why can't we feel it here on Earth? A field with enough energy to accelerate the entire cosmos should, in principle, produce measurable forces between objects in a laboratory. Yet, every sensitive experiment has come up empty. The chameleon field theory proposes a radical answer because dark energy is actively hiding from us. Imagine a field that is not uniform and passive, but acutely aware of its surroundings. Its strength and its influence are not fixed. In the dense, matter-rich environment of our planet, surrounded by walls and air and equipment, the chameleon field becomes incredibly feeble and short-ranged. It effectively screens itself, shrinking its influence to remain undetectable amidst the crowd of ordinary atoms. It blends into the background, just like its namesake reptile changes color to match the leaves. But in the vast, near-perfect vacuum of intergalactic space, where matter is spread thinner than a single atom in a football stadium, the field has nothing to hide from. Here it can stretch out, revealing its full, repulsive strength. It becomes the dominant force pushing galaxies apart. This screening mechanism is a clever loophole. It means the chameleon field could be incredibly powerful on cosmic scales, yet so weak locally that our finest instruments miss it. Testing this idea, however, is a monumental challenge. Scientists must design experiments that can probe the field in its unscreened state. One approach is to use the universe itself as a laboratory. They look for subtle distortions in the shapes of distant galaxies, searching for signs that the chameleon field is subtly altering the path of light in the voids between galaxy clusters where it should be strongest. Another, more daring idea involves bringing the vacuum of space down to Earth. By creating an ultra-high vacuum chamber and suspending a tiny, exquisitely sensitive test mass inside, researchers hope to detect the faintest whisper of a force that only appears when matter is almost entirely absent. The implications of a chameleon field reach beyond dark energy, touching the very nature of gravity itself. If confirmed, it would be a form of modified gravity, suggesting that Einstein's theory, while brilliantly accurate in our solar system, might need adjustment in the extreme low-density environments of the cosmic web. It proposes that what we call dark energy may not be a mysterious substance, but a signature of gravity behaving differently on the grandest stages of all. Einstein's gravity paints a picture of space as a smooth, flexible sheet, bent by mass like a bowling ball on a trampoline. But what if that sheet can also be twisted? This is the core idea of Einstein-Cartan theory, a profound extension of general relativity that introduces a new hidden field, the torsion field. In this more complete geometry, spacetime is not just curved, it can possess an intrinsic twist like a coiled spring woven into its very fabric. This twist is not caused by mass or energy, but by something more fundamental, the spin of particles. every electron, every quark spins on its axis, a tiny quantum gyroscope. In standard physics, this spin is just a property the particle carries. But in Einstein-Cartan theory, this microscopic spin generates a microscopic twist in the geometry of spacetime itself. It is as if each spinning particle is a tiny drill bit, imparting a local corkscrew motion to the fabric of reality. This torsion field is incredibly weak under normal conditions, completely drowned out by the effects of mass and energy. You cannot feel the twist from the spinning electrons in your hand, but in the extreme environments of the universe's birth or its most destructive objects, torsion could become the lead actor. In the seething density of the very early universe, where matter was packed unimaginably tight, the combined spin of countless particles could have generated a cosmic torsion field of significant strength. This twisting force might have acted as a kind of repulsive pressure, helping to drive the initial expansion of the cosmos and perhaps even seeding the rotation we see in galaxies today. It offers an elegant link, a hidden geometric field born from particle spin directly influencing the largest structures we observe. Perhaps the majestic spiral arms of galaxies are an echo of that primordial twist imprinted on the cosmos. The implications grow even more dramatic inside black holes. In general relativity, the heart of a black hole is a singularity, a point of infinite density where the laws of physics break down. It is a place where our understanding ends. Einstein-Cartan theory provides a possible escape from this cosmic dead end. As matter collapses to form a black hole, the spin of particles becomes ever more concentrated. The resulting torsion field grows in strength, and according to the math, it can produce a repulsive force so powerful that it halts the collapse before a true singularity forms. Instead of a point of infinite density, you might get a highly dense spinning core, a place where matter is rebounded into a new state, or even a gateway to another region of spacetime. This suggests that black holes are not ultimate endpoints but cosmic transformers, their hidden internal geometry shaped by the ghostly torsion field generated by every spinning bit of matter that fell in. While not yet part of mainstream cosmology, the theory compels us to see the universe not as a passive stage, but as an active participant, its geometry dynamically shaped by the quantum spin of its smallest constituents. It is a reminder that the secrets of the cosmos may be written not just in the language of gravity, but in the silent, twisting dance of spacetime itself. But gravity's hidden geometry is not just about static curves or subtle twists. It can also create invisible whirlpools in the fabric of reality. This is the gravitomagnetic field, a hidden component of gravity predicted by Einstein's equations that behaves in a way eerily similar to magnetism. You are familiar with how a moving electric charge creates a magnetic field. In the same way, general relativity tells us that moving mass, or more specifically, rotating mass, generates a gravitational analog. A spinning planet or star doesn't just curve the spacetime around it, it also drags that spacetime into a slow, cosmic swirl. Imagine a heavy ball submerged in a thick fluid like honey. If you simply place the ball in the honey, it creates a depression that is the standard curvature of gravity. But if you start to spin the ball, it will pull the surrounding honey into a circular motion around itself. The honey closest to the ball moves faster while the honey farther out lags behind. This is the essence of frame dragging, also known as the lens-thirring effect. The rotating mass literally tugs the very grid of spacetime into rotation with it. For an object like Earth, this effect is incredibly subtle. The planet's spin drags spacetime around it by a minuscule amount, roughly equivalent to moving a satellite by the width of a human hair over the course of a year. Yet this tiny whisper of a force is a direct prediction of Einstein's theory, and measuring it became one of the most precise experiments in the history of science. That mission was Gravity Probe B. Launched in 2004, it was a technological marvel. At its heart were 4 ultra-precise gyroscopes, each a spinning sphere of fused quartz coated with superconducting niobium and polished to be the most perfect spheres ever manufactured by humanity. These gyroscopes were housed in a satellite orbiting 400 miles above Earth, pointed at a distant guide star. In a universe without frame dragging, the axes of these gyroscopes would have remained locked perfectly on that star forever. But if Einstein was right, the gentle whirlpool of spacetime created by Earth's rotation would very slowly tilt the direction of the spin axis. After 17 months of painstaking data collection, accounting for myriad other tiny disturbances, the results were in. The gyroscopes had drifted. The drift matched Einstein's predictions with remarkable precision, confirming that our planet does indeed drag the fabric of reality around as it turns. This was not just a validation of a century-old theory, it was a direct measurement of a hidden field in action. The gravitomagnetic field is not some exotic add-on, it is woven into the very definition of gravity. Its confirmation means that near any massive, rotating object, a neutron star, a black hole, a galaxy, the rules of motion are subtly altered by this invisible current. The orbits of objects are not just ellipses, they are precessing spirals influenced by the space-time vortex. This hidden component of gravity may hold keys to understanding the violent dances of binary black holes and the powerful jets screaming from the cores of active galaxies. It reveals a universe where mass does not merely tell space how to curve, but motion tells spacetime how to swirl. Yet these swirling currents of gravity are governed by deeper, more fundamental rules. Beneath the dance of particles and the geometry of spacetime lies an invisible architecture of symmetry, a hidden order so perfect it might dictate the very laws of physics. This leads us to symmetry fields and a staggering possibility they imply: the multiverse. In physics, symmetry is not just about beauty, it is about invariance, the idea that certain properties remain unchanged even when you rotate, mirror, or otherwise transform a system. The most profound symmetries are believed to be enforced by hidden fields. The Higgs field, for instance, is linked to a broken symmetry, a once perfect state that fractured as the universe cooled, giving particles mass. But what if other, even more fundamental symmetry fields exist? Fields whose stable states literally define the strength of gravity, the mass of an electron, or the charge of a proton. This is where string theory enters the stage, painting a picture of reality with 10 or more dimensions. In this framework, the extra dimensions are curled up into fantastically tiny, complex shapes. The way they are curled determines how the vibrational strings within them behave, which in turn sets the physical laws and constants we observe. But there is not just one way for these dimensions to curl. In fact, string theory suggests a staggering number of possibilities, perhaps 10 to the 500 or more. This is the cosmic landscape. Each stable configuration, each possible valley in an unimaginably complex energy terrain, represents a different vacuum state for the universe's hidden fields. And each vacuum state corresponds to a universe with a unique set of physical laws. In this view, our universe, with its specific constants fine-tuned for stars, planets, and life, is just one possibility among a near infinity of others. The mechanism for generating these alternate realities could be tied directly to cosmic inflation. During that period of hyper-expansion driven by the inflatoned field, quantum fluctuations were not just stretched into galaxies, they could have caused the symmetry fields to tunnel or settle into different vacuum states in different regions of the inflating spacetime. Picture a pot of water coming to a furious boil. Bubbles of steam form at different points, each expanding rapidly. In our cosmic analogy, each bubble is a region where the hidden symmetry fields have randomly fallen into a particular stable state, defining its own unique physics. As inflation ends in that bubble, it becomes a separate, causally disconnected universe within a vast, frothy multiverse. Our entire cosmos would be just one bubble in an endless, effervescing foam of realities. The mind-bending visuals this conjures are not of separate galaxies, but of separate spacetimes, each a self-contained universe with its own laws, some where gravity is stronger, some where atoms cannot form, some where time flows backward, and perhaps a rare few where conditions are just right for consciousness to emerge and wonder about it all. The symmetry fields then become the ultimate authors, and their random choices during creation wrote not one story but an infinite library of them. The infinite library of the multiverse suggests a universe of staggering complexity, but what if all that complexity is merely a surface illusion? This brings us to one of the most profound and radical ideas in modern physics, the holographic principle, and the hidden information field it implies. At its heart is a deceptively simple claim: all the information needed to describe everything within a three-dimensional volume of space is actually encoded on its two-dimensional boundary. Imagine a science fiction hologram, a shimmering, three-dimensional figure that seems to float in mid-air. Yet that entire figure, with all its depth and detail, is projected from a flat, two-dimensional surface like a special film or glass plate. The holographic principle suggests our universe might operate on a similar but far more fundamental level. The three-dimensional reality we experience, with its galaxies, planets, and people, could be a magnificent projection from a vast, two-dimensional surface at the edge of the cosmos. This isn't about literal light projections, but about information. Every particle, every force, every event happening in the bulk of space is translated into bits of data painted onto this cosmic boundary. You are not just in the universe, you are a translation of information written on its farthest skin. This staggering idea emerged not from speculation about the cosmos, but from the paradoxical nature of black holes. In the 1970s, physicist Jacob Bekenstein made a crucial connection. He realized that a black hole's entropy, a measure of its hidden information or disorder, is proportional not to its volume, but to the area of its event horizon. This was bizarre. For any ordinary object, entropy scales with volume. A larger box can hold more disordered stuff than a smaller one. But for a black hole, the ultimate trap for information, the maximum information it can contain is defined by the surface area of its spherical point of no return. It was as if all the data about everything that ever fell in was compressed and stored on that two-dimensional surface like a cosmic hard drive. Later, string theorists like Leonard Susskind and Gerard T. Hooft took this insight and universalized it. They proposed that this area law for information isn't just a quirk of black holes, it is a fundamental law for all of spacetime. The universe itself might be a hologram. In this view, the true, fundamental reality is a vast, shimmering network of information on a distant boundary we cannot see. Our familiar world of three spatial dimensions is a grand, dynamic illusion generated from that data. The forces we feel, the particles we are made of, are like the pixels and colors of a three-dimensional movie rendered in real time from a two-dimensional script. This implies the existence of a hidden information field, the fundamental substrate where the code of reality is written. The equations that govern our universe would not be the final story. They would be the user interface, the emergent laws that arise from the deeper processing of information on the boundary. Testing such a mind-bending concept might seem impossible, but physicists are looking for subtle signatures. Some models suggest that if the holographic principle is true, there should be a faint, universal fuzziness or limit to the precision of all measurements at the tiniest scales, a graininess to spacetime itself imposed by its pixelated origin. Others search for correlations in the cosmic microwave background that might hint at an underlying two-dimensional structure. The holographic principle forces a complete reimagining of existence. It suggests that the deepest reality is not made of stuff, but of relationships, of information woven into a hidden field from which all of space, time, and matter are projected. We are not just living in a universe, we are living inside a cosmic calculation. The holographic universe suggests reality is a projection, but what about the projector itself? if space can be an emergent property, could time be as well? This leads us to a profound question. Is time a fundamental river, or is it something that merely trickles from a deeper source? Some physicists suspect time itself is not continuous but granular, built from tiny, indivisible moments. The speculative field that would govern these moments is called the chronon field, and its existence would rewrite our understanding of causality itself. In our daily experience, time flows smoothly from one instant to the next, but at the Planck scale, the realm of quantum gravity, this smoothness may shatter. Just as a digital photograph reveals pixels when you zoom in far enough, spacetime might be composed of fundamental atoms of time and space. A chronon would be the smallest possible unit of time, perhaps around 10 to the minus 43 seconds, the time it takes light to cross a Planck length. In this view, the chronon field is the underlying framework, a kind of cosmic metronome ticking out the discrete steps of reality. One theory that embraces this idea is causal set theory. It proposes that the fabric of the universe is not a smooth continuum, but a vast collection of discrete events like grains of sand. Each event is linked to others in a network of cause and effect. This caused that. The smooth geometry of spacetime, the curves and bends of Einstein's universe, would then be a large-scale approximation, an average emerging from the frenetic connections in this underlying network. It is like watching a movie. The illusion of continuous motion emerges from a rapid sequence of still frames. The chronon field would be the director of this cosmic film, determining the order and rhythm of each frame. The philosophical implications are staggering. If time is granular and emergent, then the relentless forward arrow of time, the feeling of past, present, and future, might also be an illusion born from this complex network. Our conscious experience of duration, of one moment seamlessly becoming the next, could be a trick played by a brain processing a universe that is, at its core, a sequence of frozen instants. This challenges the very essence of free will and destiny. Are we moving through time, or is time, with all its apparent history and future, simply the structure of a vast, static causal network we are traversing? Testing such an idea is monumentally difficult as these chronons are unimaginably small. However, some experiments look for the faintest signatures of a pixelated reality. Ultra-precise measurements of the speed of light over vast distances, or observations of extremely high-energy gamma rays from distant cosmic explosions, might reveal a subtle graininess if the energy of the photons is high enough to feel the discrete structure of spacetime. Finding evidence for the chronon field would be a revolution. It would mean that time, the stage upon which all events play out, is itself a secondary character, emerging from a hidden, timeless order of connection and information. The universe would not be a movie playing on a screen of spacetime, but a cosmic flipbook, its story told one fundamental tick of the chronon field at a time. If time itself can be an emergent illusion, what about the observer experiencing it? We have journeyed through fields that shape matter and bend space, but one profound mystery remains untouched, the spark of awareness itself. This leads us to the most speculative and ethereal of all hidden fields, the psychon field. This is not a concept from established physics, but a daring hypothesis from the edges of philosophy and theoretical science. It proposes that consciousness, the very essence of subjective experience, might not be a mere byproduct of complex brain chemistry. Instead, it could be a fundamental property of the cosmos, as intrinsic to reality as mass or charge, mediated by its own hidden field. The idea finds roots in ancient philosophies, but its modern incarnation is often linked to panpsychism. This view suggests that consciousness, in some extremely basic form, is a universal ingredient. Just as electrons possess charge and mass, they might also possess a minuscule degree of raw experience or proto-consciousness. In this picture, the universe is not dead matter suddenly coming to life, but is alive or at least sentient at every level. A rock would not think, but the fundamental fields and particles composing it might hold a faint whisper of subjective being. The cyclone field, then, would be the medium through which these elemental whispers combine and integrate. Think of it like sound. A single molecule of air moving makes no audible noise, but trillions upon trillions of molecules vibrating in a coordinated pattern create a symphony. Similarly, the theory suggests that the simple, fundamental consciousness associated with particles, when organized into the staggeringly complex network of a human brain, integrates through this field into the rich, flowing stream of thoughts, feelings, and sensations you are having right now. This integration is echoed in a more formal framework known as Integrated Information Theory, or IIT. While not explicitly requiring a field, IIT proposes that consciousness corresponds to a system's capacity to integrate information. The more interconnected and differentiated a network is like the human brain, the higher its level of conscious experience. A cyclone field could be the physical mechanism that allows for this integration, a hidden channel that binds disparate signals into a unified whole. The scientific skepticism here is immense and warranted. There is no experimental evidence for such a field, no way to measure a unit of consciousness, and it currently lies far outside the testable methods of physics. Critics argue it is a solution in search of a problem, adding a mysterious new layer to explain something neuroscience is diligently mapping. Yet, the philosophical allure is undeniable. It offers an elegant bridge between mind and cosmos, resolving the so-called hard problem of consciousness, why physical processes should feel like anything at all. If consciousness is fundamental, then our inner world is not an accidental ghost in the machine, but a direct expression of the universe's hidden nature. We are not just beings within the cosmos, we are the cosmos becoming aware of itself, through a field that connects the faintest glimmer of experience in a quark to the profound wonder of a human gazing at the stars. But if consciousness is a fundamental field, it exists within a universe bound by a cosmic speed limit, the speed of light. Or is it, beyond the horizon of light lies one of physics' most provocative ideas, the tachyon, a particle born from a field of pure instability? In the equations of quantum field theory, there exists a strange possibility, a solution where a particle's mass squared is a negative number. This mathematical oddity describes the tachyon field, and its associated particle would have a truly bizarre property. It must always travel faster than light. It cannot slow down to the speed of light or below, just as we cannot accelerate ordinary matter to reach that ultimate barrier. The name itself comes from the Greek word for swift. Think of it like this: ordinary particles are like boats in water. They can move at various speeds up to a maximum, creating a wake. Light is like a speedboat hitting its precise top speed. A tachyon, however, would be like a plane already in the air. It only exists in the realm of speeds beyond that water-bound limit. In many theoretical models, the tachyon field is not a stable, enduring feature of our cosmos. Instead, it represents a state of precarious, high energy. A system in a tachyon field configuration is like a pencil balanced perfectly on its tip, a state of unstable equilibrium. The slightest perturbation would cause it to roll violently into a stable state, a process called tachyon condensation. This is where the idea moves from curious math to cosmic storytelling. In the very early universe, during the frantic moments of cooling after inflation, some theories suggest certain fields might have briefly existed in this tachyonic state. This instability would have triggered a catastrophic universe-wide phase transition. As the tachyon field condensed and rolled down its energy hill, it would have released immense energy, potentially reshaping the forces of nature and giving mass to particles in a process even more fundamental than the Higgs mechanism. Some string theories use tachyons to describe the decay of unstable, higher-dimensional objects called D-branes, whose collapse could have sparked the birth of our three-dimensional reality. Yet for all its theoretical utility, the tachyon brings with it a storm of paradoxes. The most famous is a violation of causality, the principle that cause must always precede effect. If a signal can travel faster than light, then in some frames of reference, that effect could be observed before its cause. Imagine a tachyon message sent from Earth to a distant star. From the perspective of a spaceship moving at a certain high speed, that message could appear to arrive at the star before it was even sent from Earth. This opens the door to logical nightmares, like sending a signal back in time to prevent your own birth. Because of these profound contradictions with the logical order of the universe, most physicists believe that if tachyons exist at all, they cannot be used to transmit information or energy. They would be ghostly mathematical entities, perhaps flashing in and out of existence in the quantum foam, forever locked in their superluminal realm, unable to interact coherently with our slower-than-light world. Their lasting legacy may be as a signpost, a mathematical flare indicating a state of profound transition, a hidden field whose instability once shook the foundations of everything, forcing the infant cosmos to choose the stable, causal reality we now call home. That cosmic instability once forced a choice, but what if the very rules of the game are still slowly changing? Hidden within the extra dimensions of string theory is a field whose whispers could rewrite the textbook constants of physics, the dilaton field. In our quest for a theory of everything, physicists seek a single framework to unite gravity with the other fundamental forces. String theory attempts this by proposing that all particles are vibrations of tiny, one-dimensional strings. The nature of these vibrations, and thus the particles and forces they become, depends crucially on how the extra dimensions are curled up. But there is a master dial that controls the overall scale of this compactified geometry, and that dial is set by the dilaton field. Think of it as the cosmic volume knob for the strength of gravity itself. Where the dilaton field has a certain value in space, that value determines how tightly the extra dimensions are wound, which in turn sets the coupling constants for all forces, from electromagnetism to the strong nuclear force. In many models, the dilaton is a scalar field, much like the Higgs, meaning it has a value at every point in space rather than a direction. The revolutionary and unsettling implication is this: if the dilaton field is dynamic, not frozen, then the so-called constants of nature might be anything but constant. They could be slowly evolving as the universe expands and cools. The fine structure constant, a pure number that dictates the strength of the electromagnetic force, would be a prime candidate. This number controls how tightly electrons bind to atomic nuclei, the energy of chemical reactions, and the very color of light emitted by atoms. If it were even a few % different, stars could not fuse carbon, molecules would not form, and life as we know it would be impossible. Yet, if the dilaton field has been slowly rolling toward its minimum over billions of years, this sacred constant might have been subtly different in the distant past. Astronomers are hunting for this cosmic drift by turning the universe into a time machine. They point powerful telescopes at the most luminous objects in the distant cosmos, quasars, whose light has traveled for over 10 billion years to reach us. As this ancient light passes through clouds of interstellar gas on its journey, specific atoms within those clouds absorb very precise wavelengths, leaving dark lines in the quasar's spectrum like a barcode. If the fine structure constant had a different value when that light was absorbed, the spacing between those barcode lines would be minutely shifted. Teams have analyzed hundreds of these quasar spectra, and some have reported tantalizing, controversial evidence of a very slight variation, a few parts in a million, across vast regions of space. The debate is fierce as the measurements push against the limits of our instruments and require incredibly complex calibrations. If confirmed, it would be a discovery of Nobel Prize magnitude, shattering the assumption of immutable laws. It would mean the universe in its youth played by slightly different rules, with gravity perhaps being stronger or electromagnetism weaker. Visualize a cosmic timeline not just of expanding space and cooling temperatures, but of shifting fundamentals, where the forces that sculpt reality wax and wane in strength over eons. A dynamic dilatant field offers a breathtaking vision, a living universe where the laws themselves are written in fading ink, slowly settling into the familiar patterns we measure today, hinting that our current reality is just a temporary chapter in an epic story of transformation. While the dilatant field tunes the cosmic constants, another hidden actor in string theory's 10-dimensional stage governs the very way strings twist and connect. This is the Kalb-Rammond field, a force so strange it defies the geometry of our familiar world. To understand it, we must first visualize a string not as a particle but as a tiny, vibrating loop or segment. Just as an electron carries an electric charge that allows it to feel the electromagnetic field, a string carries a charge that lets it interact with the Kalb-Rammond field. But here is where the analogy twists. The electromagnetic field is described by a vector, an arrow with direction and magnitude, like the force pointing from a positive to a negative charge. The Kalb-Rammond field, however, is an antisymmetric tensor field. In simpler terms, it is not about arrows but about oriented areas. Imagine a tiny, two-dimensional tile, a microscopic door. The field assigns a number to that tile, a strength, but with a crucial quirk: if you flip the orientation of the tile, the number flips its sign. This peculiar geometry means the field naturally couples to the world sheet of a string, the two-dimensional surface a string sweeps out as it moves through spacetime. When strings interact, they can merge or split, their world sheets joining like soap bubbles combining. The Kalb-Rammond field influences these interactions, guiding how strings weave together in the hidden dimensions. In our four-dimensional reality, this exotic field reveals a surprising connection to forces we already know. When the extra 6 dimensions of string theory curl up into intricate shapes called Calabi-Yau manifolds, the Kalb-Rammond field gets projected down onto our familiar spacetime. Some of its components behave exactly like the electromagnetic field, offering a potential unified origin for light and other forces. Other components manifest as a field that gives rise to torsion, that twisting of spacetime we explored earlier in Einstein-Cartan theory. Even more intriguing, certain vibrations of the Kalb-Rammond field in the coiled-up dimensions could produce particles with all the properties of the axion, that leading dark matter candidate. In this way, a single, multidimensional hidden field could be the secret parent of several seemingly unrelated phenomena in our four-dimensional world. The reason we do not feel its full, bizarre geometry is because those extra dimensions are compactified, curled up at scales a billion times smaller than an atom. We are like flatlanders living on a vast sheet, completely unaware that our sheet is actually the surface of a thin straw, with a tiny, circular dimension curled around it. All the rich, multi-directional dance of the Kalb-Rammond field happens in those unseen, compact directions, leaving behind only its shadow in our universe as familiar forces and potential new particles. Its existence suggests that the deepest layer of reality is not made of points, but of extended objects interacting through a geometry of surfaces and volumes, a hidden choreography that writes all the laws we experience. The luminiferous ether was a ghost we thought we had banished. In the late 19th century, physicists believed light waves needed a medium to travel through, just as sound needs air. They envisioned an invisible, static substance filling all of space, the ether. The famous Michelson-Morley experiment in 1887 sought to detect Earth's motion through this cosmic sea. They found nothing, the ether did not exist, and Einstein's theory of relativity cemented the idea that light needs no medium, space itself is the stage. Yet, a century later, quantum mechanics has resurrected the ether in a far stranger, more dynamic form. We now call it the quantum vacuum, and it is anything but empty. What we perceive as nothingness is in fact a seething, frothing ocean of energy, According to quantum field theory, every point in space, even in a perfect vacuum, is alive with activity. So-called virtual particles, pairs of matter and antimatter, constantly wink into existence, borrowing energy from the vacuum itself for an unimaginably brief moment before annihilating each other and vanishing back into the void. This is not a metaphor, it is a direct prediction of Heisenberg's uncertainty principle, which allows for such fleeting violations of energy conservation. The vacuum is not a still pond, but a boiling pot with particle-antiparticle pairs bubbling up and popping every instant. This modern ether, this quantum vacuum energy, has a profound and measurable presence. Its effects are not just theoretical curiosities, they shape the very behavior of atoms. Consider the Casimir effect. Take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum, just a few nanometers apart. Classically, nothing should happen, but in the quantum world, the space between the plates restricts the kinds of virtual particles that can pop into existence. Only certain wavelengths fit. Outside the plates, the vacuum can host a fuller spectrum of these fluctuations. The result: the virtual particles outside push the plates together with more force than those between them can push apart. A tiny, measurable force pulls the plates together, as if the ghostly pressure of the quantum ether itself were squeezing them. This has been experimentally confirmed. Even more telling is the Lamb shift, a subtle change in the energy levels of the electron in a hydrogen atom. According to Dirac's original equations, two specific energy states should be identical. But in 1947, Willis Lamb and Robert Rutherford found a tiny split, a minute difference. The explanation: the electron is constantly jostled by the quantum foam of the vacuum. These virtual particles buffet the electron, slightly altering its path and energy, like a tiny boat being rocked by an invisible, chaotic sea. This shift is precisely predicted by quantum electrodynamics and stands as one of its great triumphs. So the ether is back, but not as a static, preferred frame. It is a dynamic, omnipresent field of zero-point energy, the lowest possible energy state of a quantum field, which is still full of frantic activity. This hidden field is not a medium for light to wave through, but the fundamental ground state of reality itself, a canvas of pure potential from which every particle momentarily springs and into which it dissolves. It suggests that what we call empty space is the most rich and active thing in the universe, a hidden ocean whose waves are the particles of existence. This quantum sea underpins all matter, yet life seems to dance to a different, more mysterious rhythm. From a single cell, an organism unfolds into a breathtakingly complex form: a human hand, a leopard spots the fractal branching of a fern. How does this happen? The blueprint in our DNA provides the chemical instructions, but some argue it cannot fully explain the exquisite coordination in space and time. One radical answer lies in the theory of morphic fields, proposed by biologist Rupert Sheldrake. This idea ventures beyond physics into biology and mind. A morphic field is a non-physical, invisible template that guides the development and behavior of living things. Think of it as a kind of cosmic habit. The first time a new protein folds or a new species evolves, the process is slow and uncertain. But according to Sheldrake, each successful occurrence creates a morphic resonance, strengthening the field and making it easier for the same pattern to happen again, anywhere in the world. It is a theory of formative causation, where the past literally shapes the present through these hidden fields. Morphogenesis, the process by which an embryo takes shape, is the classic example. DNA provides the building blocks, like bricks and mortar for a house. But the morphic field would be the architect's blueprint, the organizing principle that tells the bricks exactly where to go to form walls, windows, and doors. This field would guide cells to differentiate, migrate, and connect, orchestrating the emergence of form from apparent chaos. Even more controversially, Sheldrake extends this idea to collective behavior and memory. Have you ever felt that as more people learn to solve a certain puzzle, it seems to become easier for others to solve it later? Or consider how flocks of birds or schools of fish move with such perfect, instantaneous synchronization, as if guided by a single mind. The morphic field theory suggests they are connected by a shared, non-local field of information, a kind of species-wide memory that transcends individual brains. This is not telepathy in the psychic sense, but a natural resonance within a biological field. The scientific establishment has largely rejected this theory, and for strong reasons. It is notoriously difficult to test in a way that rules out all conventional explanations. Critics argue it is vague, untestable, and unnecessary, as gradual evolution and complex biochemical signaling can explain the development and behavior Sheldrake attributes to morphic resonance. Mainstream biology sees no evidence for a non-physical field carrying information. Yet, as a what-if scenario, it remains a fascinating thought experiment about the nature of habit and form in the cosmos. It asks us to consider if the universe learns, if patterns themselves have a kind of inertia, and if memory might be a property not just of brains but of the fabric of reality. Visualize a time lapse of a growing embryo, its cells swirling and dividing not at random, but as if pulled by an invisible mold, a pre-existing shape made not of matter but of pure potential. It is a vision where life is not just a chemical accident, but a participant in a hidden field of formative memory, drawing upon the accumulated habits of everything that has lived before. But what if the collective memory of life is not just a passive record, but an active, evolving layer of the planet itself? From the morphic fields of biology, we step into a grander vision, the noosphere. This is the theory of a thinking layer of Earth, a sphere of human thought and consciousness that has grown to envelop the biosphere just as the biosphere envelops the geosphere. The term was coined independently by two visionary thinkers, the French philosopher and paleontologist Pierre Teilhard de Chardin and the Russian geochemist Vladimir Vernadsky in the early 20th century. They saw a profound progression in our planet's history, first the lifeless rock of the geosphere, then the explosion of life creating the biosphere, and now, with the advent of humanity, the emergence of a new thinking membrane, the noosphere. In this view, our networks of ideas, culture, science, and communication are not just social constructs. They are a geological force, a new kind of planetary field. Visualize Earth not just as a blue marble, but as a globe encircled by a shimmering, luminous net, a web of light representing every phone call, every internet packet, every broadcast signal, every shared thought and piece of knowledge flowing between billions of minds. This glowing mesh is the visible signature of the noosphere, a potential hidden field of collective human intelligence. Teilhard de Chardin, in particular, saw this as a spiritual and evolutionary destiny. He believed that as human interconnection deepened, the noosphere would tighten and intensify, leading toward a point of ultimate convergence he called the Omega Point, a state of unified collective consciousness. While his framework was theological, the underlying idea finds startling echoes in modern secular concepts. The Gaia hypothesis proposed by James Lovelock suggests the biosphere itself acts like a self-regulating organism. Extend that idea to include the human mind, and you approach a vision of a planet that is not only alive but aware through us. Today, with the instantaneous global connectivity of the Internet, the metaphor of a global brain is more tangible than ever. The noosphere can be seen as the informational field generated by this planetary neural network. Our digital devices act like synapses, firing signals across the globe at the speed of light. Social media trends, financial markets, and the rapid spread of scientific discoveries all behave with a complexity that seems to transcend any individual, hinting at an emergent intelligence of the network itself. Could there be a literal, if subtle, field underlying this? It is a profound speculation. Some theorists propose that if consciousness is fundamental, as the cyclone field hypothesis suggested, then the concentrated, interconnected consciousness of 8 billion humans might generate a coherent field effect, a resonance that subtly influences thought patterns, cultural shifts, and perhaps even the physical environment. This is not about telepathy, but about a shared informational landscape that becomes a new kind of ecological niche, shaping our evolution as powerfully as any forest or savanna once did. The noosphere represents the ultimate hidden field of human making, a testament to the idea that our thoughts, when woven together, become a new geological layer, a thinking skin on the world, and perhaps the next great transition in the story of our planet. This shimmering noosphere is built upon a foundation of energy, but that foundation itself might hold a secret reservoir of almost infinite power. The quantum vacuum, that modern ether, is not just a chaotic sea of virtual particles. It is a field with a specific, irreducible minimum energy, even at the temperature of absolute zero. This is the zero-point field, the ground state of the universe. According to quantum mechanics, a field can never be perfectly still. It must always possess a tiny residual jitter, a fundamental hum of existence. This zero-point energy is not a speculative idea. It is a required feature of our most successful theories, evidenced in effects like the Casimir force and the Lamb shift. Yet its sheer magnitude is staggering. Crude calculations summing up all possible vibrational modes in a cubic centimeter of empty space yield an energy density so enormous it could boil away Earth's oceans in an instant. This number is so absurdly large that physicists believe it must be cancelled out by other effects, or our understanding of gravity at quantum scales is profoundly incomplete. Still, the raw potential whispers a tantalizing question: could this hidden field be tapped? The dream of zero-point energy, or free energy, has captivated inventors and fringe theorists for decades. They envision devices that could somehow extract useful work from this ubiquitous background hum, offering limitless, clean power drawn directly from the fabric of space itself. Imagine a machine not powered by fuel, sunlight, or wind, but by the quiet vibration of the vacuum, a shimmering apparatus that somehow rectifies the quantum noise into a steady current. The visual is compelling, a crystalline device glowing with an inner light connected to nothing, yet powering a city. The allure is undeniable, a solution to every energy crisis, a key to interstellar travel. It speaks to a deep human desire to find a hidden generosity in nature. However, mainstream physics presents a formidable wall of thermodynamic objections. The zero-point field is in its lowest possible energy state by definition. You cannot draw energy from a system already at its ground state without lowering it further, which is impossible. Think of it like a perfectly flat lake. You cannot use the water in a flat lake to turn a water wheel. You need a difference in height, a gradient. The zero-point field, as we understand it, is that flat lake everywhere. Any hypothetical device would need to create a local depression, a lower energy state than the ground state, which thermodynamics forbids. Furthermore, the zero-point energy is not a hidden battery. It is the baseline, the zero on the cosmic meter. Using it for work would be like trying to power a car by collecting the heat from its own engine, a perpetual motion machine of the subtlest kind. While speculative concepts like the Casimir effect show that the energy density can be manipulated between plates, harvesting net energy from such a setup remains theoretically dubious. The chasm between the dream and established physical law is vast. Yet, the persistence of the idea highlights a profound truth: our universe is not empty, and its deepest ground state thrums with a hidden activity. Whether it can ever be a wellspring remains one of physics' most captivating mirages, a siren song calling from the quantum void. The mirage of zero-point energy speaks to a universe that is never truly idle, but the idea of continuous creation takes that restlessness to its ultimate conclusion. In the mid-20th century, as evidence mounted for an expanding universe, a profound question emerged. If space is stretching and galaxies are flying apart, why does the cosmos not simply thin out into an eternal, featureless void? The dominant answer, emerging from the work of Georges Lemaitre and George Gamow, was the Big Bang, a singular explosive origin from a hot, dense state. But a trio of brilliant astronomers, Fred Hoyle, Thomas Gold, and Hermann Bondi, proposed a radically different vision. They championed the steady-state theory, an eternal universe with no beginning and no end, forever maintaining the same average density. To make this work, they needed a hidden field, a mysterious, gentle force that would continuously create new matter from nothing. Hoyle called this the C field, the creation field. Picture a universe not with a dramatic beginning, but in a state of perfect balance, like a timeless forest. As old trees die and fall, new seedlings spontaneously sprout to take their place, keeping the overall density of the forest constant. In the cosmic version, as galaxies drift apart due to expansion, the C field would gently trigger the formation of new hydrogen atoms in the vast voids between them. These atoms would eventually coalesce into new stars and galaxies, filling in the gaps so that the overall picture of the cosmos on the largest scales would always look the same. It was an elegant, even beautiful idea, offering an infinite, unchanging stage for existence, free from the theological and philosophical baggage of a moment of creation. The C field was not a violent event, but a subtle, ongoing process, a hidden trickle of genesis woven into the fabric of space itself. The theory made clear predictions, most importantly that the universe should look statistically identical in every era. Distant regions whose light has taken billions of years to reach us should show galaxies similar to those nearby. This set the stage for a great cosmological duel. The discovery that would decide the fate of the steady-state universe came not from telescopes pointed at galaxies, but from a strange, persistent hiss in a radio antenna. In 1965, Arno Penzias and Robert Wilson at Bell Labs were troubleshooting a peculiar microwave noise that plagued their sensitive horn antenna. It was uniform, it came from all directions, and it would not go away. They had quite accidentally stumbled upon the cosmic microwave background, the cooled remnant of the universe's hot, dense infancy. This was the definitive evidence the Big Bang model had predicted, the afterglow of the initial fireball. For the steady-state theory, it was a fatal blow. A universe in perfect balance, with matter continuously created, would not have such a pervasive, uniform thermal signature from a hot, dense past. There was no elegant way for the C field to explain this fossil radiation. While Hoyle and others made valiant attempts to modify the theory, the weight of evidence, including the precise blackbody spectrum of the CMB later confirmed by the COB satellite, cemented the Big Bang as the standard model. The C field faded from mainstream cosmology, a ghost of a discarded universe. Yet its legacy endures as a masterpiece of scientific imagination, a reminder that the cosmos we accept today was once one of several compelling possibilities. It proposed a hidden field not of destruction or distortion, but of gentle, perpetual genesis, an eternal breath keeping the infinite universe alive. The steady-state universe faded, but the ghost of its failed prediction, the missing matter in galaxies, refused to be ignored. This enduring puzzle led to a bold and radical rebellion against the very need for dark matter. It is called modified Newtonian dynamics, or MOND, and its relativistic soul is the tensor vector scalar field, or TVS. The problem is stark and beautiful. When we observe spiral galaxies, the stars and gas in their outer regions orbit far too quickly. According to Newton's laws of gravity, which work perfectly within our solar system, these distant stars should be flung into intergalactic space. The fact they are not suggests either there is a vast halo of invisible dark matter holding them in, or our understanding of gravity itself is incomplete on the scale of galaxies. MOND chooses the second path, proposed by physicist Mordechai Milgrom in the 1980s. It suggests that gravity does not weaken with the square of distance in the extremely weak accelerations found at galaxy edges. Instead, it transitions to a different regime, weakening less sharply. It is as if gravity has a low gear, a persistent tug that becomes important only when its pull falls below a certain, incredibly faint threshold. This simple modification, defined by a single new constant, can astonishingly reproduce the flat rotation curves of many spiral galaxies without a single particle of dark matter. The stars speed up, reach a plateau, and stay there, all dictated by the visible mass alone and this tweaked law. For its proponents, it is an elegant Occam's razor, cutting away an entire universe of unseen particles. But Newton's gravity is a shadow of Einstein's. To be a complete theory, MOND needed a relativistic framework, one that could make predictions for light bending and cosmology. This is where Jacob Bekenstein, the same physicist who explored black hole entropy, constructed TVS. This theory proposes not one, but two hidden fields working alongside the familiar tensor field of Einstein's gravity. First, a scalar field, a number at every point in space that can vary, much like the dilaton. Second, a vector field, which has a direction like an arrow at each point. In TVS, the dance of gravity is a trio. The tensor field describes the standard curvature of spacetime. The scalar field modifies the strength of gravity in a way that mimics MOND's behavior in weak fields. The vector field ensures causality is preserved and the theory remains consistent. Together, they create a geometry where the acceleration of a star depends not just on mass, but on the combined influence of these hidden fields. The result is a universe where the phantom of dark matter is replaced by the ghost of modified geometry. Yet for all its ingenuity, TVS and MOND face severe challenges. While they excel at explaining the rotation of individual spiral galaxies, they struggle with the bullet cluster. This is a system of two galaxy clusters that have violently collided. Observations show that the hot, X-ray emitting gas, which makes up most of the ordinary matter, was slowed by the collision and sits in the middle. But gravitational lensing maps reveal the bulk of the mass, the stuff bending the light, has sailed right through and lies ahead of the gas. This is a direct visualization of dark matter behaving like a collisionless substance, separate from normal matter. It is incredibly difficult for any modification of gravity to explain how the gravity itself became separated from the visible mass that supposedly sources it. Furthermore, the precise acoustic peaks in the cosmic microwave background, the very same that doomed the steady-state model, are exquisitely fit by a universe containing cold dark matter. Reproducing this detailed pattern with a modified gravity theory like TVS requires intricate, and many say contrived, adjustments. Today, most cosmologists see dark matter as the more robust framework, capable of explaining a wider suite of phenomena from the earliest moments to the largest structures. TVS remains a brilliant and important counterpoint, a testament to human ingenuity in questioning dominant narratives. It forces us to ask if the darkness we infer is truly out there, or if it is a shadow cast by our own incomplete understanding of light's true path through the geometry of space. The fate of the cosmos may be far more violent than a slow, cold fade. Phantom energy is a theoretical form of dark energy so extreme it could end the universe not with a whimper but with a catastrophic scream. This idea emerges from a single number in cosmology, the equation of state parameter represented by the letter W. For ordinary matter, W is 0. For radiation, it is 1/3. For the simple cosmological constant, the most accepted form of dark energy, W is exactly -1. This value produces the steady, repulsive acceleration we observe today. But what if W is less than -1? What if it is -1.1 or -1.5? This is the realm of phantom energy, a hidden field with a pressure so powerfully negative it makes the cosmological constant seem gentle. The associated phantom field would possess a truly bizarre property. Its energy density would actually increase as the universe expands. Normally, when you stretch a volume, the energy within it becomes diluted. Think of inflating a balloon. The air molecules inside spread out, decreasing the pressure. But with phantom energy, the opposite happens. As space stretches, the phantom field grows stronger, its repulsive grip tightening with every passing moment. The acceleration would not just continue, it would run away with itself, becoming exponentially more ferocious over time. The ultimate consequence of this runaway field is the Big Rip, a cosmic doomsday of unimaginable violence. In this scenario, the phantom energy's repulsive force eventually overcomes every binding force in nature, from the mightiest to the most intimate. First, the phantom field's influence would swell on cosmic scales. Galaxies already drifting apart would be wrenched from their local groups with explosive force. Then, as the phantom energy density skyrockets, its effects would penetrate galactic realms. The gravitational glue holding individual galaxies together would be overwhelmed. Stars would be flung from their orbits, sent screaming into the darkening void. Next, the phantom field's power would reach into solar systems. Planets would be torn from their suns. Then it would target the stars and planets themselves. The gravitational and nuclear forces holding a star together would be defeated. The star would be shredded in a final, brilliant flash. Planets would be ripped apart, mountains torn from their foundations. In the last moments, as the phantom energy density approaches infinity, it would invade the very small. Atomic bonds would snap, nuclei would be pulled apart into protons and neutrons. Finally, spacetime itself would be torn asunder. The fabric of reality would fracture, perhaps even preventing the concept of a next moment from existing at all. The universe would end not in ice, but in a singularity of infinite expansion, a literal tearing of the cosmic stage. Is this a realistic possibility? Current observational data from supernova, the cosmic microwave background, and large-scale structure all tightly constrain the equation of state. The best measurements place W incredibly close to -1, with only tiny error bars allowing for the phantom possibility. Most cosmologists consider the simple cosmological constant the far more likely candidate. Yet, the phantom energy field and the Big Rip remain a vital part of the conversation, a stark reminder of how delicately our universe is balanced. The fate of everything may hinge on the precise value of a single number describing a hidden field we have only just begun to measure, a silent arbiter between a quiet eternity and a final apocalyptic roar. The phantom field's runaway violence reveals a cosmos balanced on a knife's edge, but the stability of reality itself depends on a more delicate trick, the origin of mass. We have already met the Higgs field, the cosmic molasses that slows particles and gives them substance. Yet there exists another, older path to mass, a clever mathematical sleight of hand that requires no cosmic molasses at all. This is the Stuckelberg mechanism, named after the Swiss physicist Ernst Stuckelberg, who proposed it in the 1930s, decades before the Higgs idea took hold. Its goal was to solve a deep puzzle in the quantum world. How can a force-carrying particle, like the photon which mediates electromagnetism, acquire a mass without destroying the beautiful gauge symmetry that defines the force? In the quantum realm, forces are transmitted by gauge bosons. The photon is massless, which is why light travels at the ultimate speed, and the electromagnetic force has infinite range. But what if we wanted a similar force that was short range, like the weak nuclear force? That would require its gauge bosons, the W and Z particles, to be very heavy. The Higgs mechanism achieves this through spontaneous symmetry breaking, the field settling into a valley and giving mass to particles as they move through it. Stuckelberg's approach was different, more direct. He introduced a new, hidden scalar field, now called the Stuckelberg field. This field does not condense like the Higgs. Instead, it performs a mathematical transformation, absorbing a specific component of the gauge field itself. Think of it like a chameleon not blending in, but actively changing the identity of another creature. Before the transformation, you have a massless gauge boson with certain polarization states. The Stuckelberg field interacts with it, effectively eating one of these polarization states and converting it into a longitudinal mode, the kind of vibration that only a massive particle can possess. The result is a new particle that behaves exactly like a massive version of the original gauge boson. In the diagrams of particle interactions, the process is elegant. A wavy line representing a massless photon enters a vertex, interacts with a dashed line representing the Stuckelberg field, and emerges as a double wavy line, a massive photon. The symmetry of the theory is preserved in a hidden way, but the particle we observe is unmistakably heavy. For a time, this was a compelling solution. So why did physics choose the Higgs field over Stuckelberg's mechanism? The answer lies in richness and prediction. The Higgs mechanism is not just a mathematical trick, it is a physical process with a dynamic field that has a tangible vacuum expectation value. This dynamism led to a spectacular prediction, the existence of a massive spin-zero particle, the Higgs boson, which was finally discovered in 2012. The Stuckelberg mechanism, in its pure form, does not predict a new, observable particle like the Higgs boson. It is a more minimalist mathematical solution. When the Higgs model was developed, it offered a fuller, more testable story that also elegantly gave mass to fundamental fermions like electrons and quarks, something the original Stuckelberg idea did not address. Consequently, the Higgs field became the cornerstone of the Standard Model. Yet, the Stuckelberg field never truly vanished. It found a second life in the shadows of theoretical extensions. In many theories of extra dimensions, like string theory or models with large extra dimensions, Stuckelberg mechanisms frequently appear. They provide a way for particles that appear massless in the higher dimensional bulk to acquire mass when projected down into our four-dimensional world, a process called the Stuckelberg-Higgs mechanism. They are also vital in certain models of dark matter, where a hidden sector gauge boson could gain a small mass via a Stuckelberg coupling to the ordinary photon, creating a dark photon with just a whisper of interaction with our world. So while the Higgs field won the battle for our universe's mass, the Stuckelberg field remains a powerful and elegant tool in the theorist's toolkit, a ghost in the mathematical machine that reminds us there can be multiple paths to the same profound truth. But a universe with mass is a universe that could have been perfectly symmetrical, with matter and antimatter in equal measure. Yet we live in a cosmos made almost entirely of matter. This is one of the greatest unsolved puzzles in physics, the Baryon asymmetry. For every billion particles of antimatter created in the Big Bang, there were 1,000,001 particles of matter. That 1 part in a billion excess is everything, the stars, the planets, and us. The question is, what hidden process tipped the scales? One of the most elegant answers lies not in particle collisions, but in the oscillations of a hidden field, the Erfolg-Dine field. Proposed by physicists Ian Erfolg and Michael Dine in the 1980s, this mechanism is a child of supersymmetry, a theoretical framework that posits every known particle has a heavier superpartner. In this rich, symmetric early universe, there exist scalar fields, fields with a magnitude but no direction, that are related to these superpartners. The Erfolg-Dine field is one such entity. In the hot, dense soup just after cosmic inflation, this field would have been displaced from its lowest energy state. Picture a marble resting not at the bottom of a bowl, but up on the rim, held in place by the intense energy of the newborn cosmos. As the universe expanded and cooled, the marble began to roll down, but with a crucial twist. The shape of the energy landscape for this field is not perfectly symmetric. It has a slight slope, a gentle bias imparted by the subtle violation of certain symmetries in particle physics. This bias is the secret. As the Erfolkdein field began its descent, it didn't just roll straight down. It started to oscillate, spiraling around the bottom of the potential like a coin spinning into a funnel. These oscillations are not just back and forth motions. They carry a charge, a kind of cosmic identity tag that distinguishes matter from antimatter. Because of the biased landscape, the field's spiral had a preferred direction, generating an overwhelming excess of one type of charge over the other. Then, as the oscillations dampened, the energy stored in this spiraling field decayed. It transformed, releasing its energy not as equal parts matter and antimatter, but predominantly as ordinary matter particles, quarks and leptons. The result was a universe flooded with a colossal surplus of matter, a one-sided creation event that set the stage for all future structure. The sheer efficiency of this mechanism is staggering. While other theories struggle to produce the observed asymmetry, the Erfolkdein field can generate an imbalance so large it actually requires subsequent processes to dilute it down to the 1 in a billion level we see. It turns a subtle bias into a cosmic landslide. This intimate connection to supersymmetry means that if experiments like those at the Large Hadron Collider ever discover super-partner particles, it would provide indirect but powerful support for this elegant Genesis story. The Erfolkdein mechanism paints a vivid picture of creation, not as a single explosion, but as a dynamic, spiraling dance of a hidden field. In the quieting aftermath of inflation, a silent oscillator began to turn, and with every rotation, it wrote the signature of our material world into the fabric of the cosmos, ensuring there would be something rather than nothing to build upon. That spiraling genesis of matter from the Erfolkdein field suggests a hidden architecture of breathtaking elegance. But what if that architecture is not just elegant but singular, a single geometric object from which all of reality is projected? This brings us to a controversial and ambitious outsider theory, geometric unity, proposed by mathematician and economist Eric Weinstein. It stands apart from the academic mainstream, not yet peer-reviewed, yet it captures the imagination as a radical attempt to redraw the map of fundamental physics. At its heart is a proposal for a new hidden framework, a master geometric structure from which Einstein's gravity, the quantum forces, and all known particles naturally emerge as different facets of a single profound shape. Weinstein calls this foundational object the observers. Think of it not as a field in the traditional sense, but as a cosmic seed crystal. In a supersaturated solution, a single, perfectly shaped seed can trigger the formation of an entire, complex crystalline structure, dictating the angles and connections of every facet. The observers is proposed to be that seed for reality. It is an 8-dimensional mathematical object, and our familiar 4-dimensional spacetime, with all its particles and forces, is theorized to be a kind of shadow or slice cast by this higher dimensional geometry. In this vision, the Higgs field, the electromagnetic field, even the fabric of gravity itself, are not separate entities. They are different vibrational modes or projections of this one unified observers. A change in the geometry here would ripple out, manifesting as a shift in particle masses or force strengths there. It is a theory of radical unification, suggesting that the cacophony of the Standard Model and general relativity are just different notes played on the same 8-dimensional instrument. The ambition is staggering, aiming to solve many of physics' grand puzzles in one sweep. Yet, this very ambition is the source of intense skepticism. The physics community operates on a currency of precise, testable predictions and mathematical formalisms that can be scrutinized line by line. Geometric unity, as presented publicly through lectures and podcasts, has not yet provided this in a form that allows for traditional peer review and validation. Critics argue it remains more of a compelling narrative than a fleshed-out, calculable theory. They point out that many previous attempts at grand unification have foundered on the rocky shores of mathematical consistency and experimental data. Furthermore, Weinstein's approach as an outsider, challenging established paradigms from beyond the walls of academia, adds another layer of controversy. The story of geometric unity, then, is as much about the sociology of science as it is about geometry. It highlights the tension between revolutionary ideas and the meticulous, often slow, process of scientific consensus. Can a paradigm-shattering theory emerge from outside the traditional channels? It is a modern echo of Einstein's own path, who developed relativity while working as a patent clerk, though his papers were swiftly subjected to the peer review of his day. Visualizing this is an exercise in abstract beauty. Picture an intricate, luminous crystal floating in a dark void, its facets glowing with different colors. From one angle, it casts a four-dimensional shadow that behaves like curved spacetime. From another angle, the same object projects a shimmering network that resolves into quarks and electrons. It is a vision of cosmic parsimony where all complexity derives from a single, hidden symmetry. Whether geometric unity ultimately becomes a landmark in physics or a fascinating footnote, it serves as a powerful reminder. Our quest to understand the hidden fields of the universe is not over. It may require not just new particles, but entirely new geometries, waiting in the conceptual darkness for their moment to be seen. A geometric seed for reality suggests a universe of profound order, but that order might hide a secret rhythm, a clock that ticks forever without ever being wound. This is the world of time crystals, a bizarre new phase of matter that shatters one of physics' most sacred assumptions, the symmetry of time itself. In our everyday experience, if you have a perfectly symmetric object like a featureless sphere and you rotate it, it looks the same. This is spatial symmetry. Time is thought to have a similar symmetry called time translation symmetry. If you take a physical system in its ground state, its lowest energy configuration, and you wait, nothing should change. The ground state should be the same now, in an hour, or in a billion years. It is the ultimate state of rest. Time crystals defy this, proposed theoretically by Frank Wilczek in 2012. A time crystal is a quantum system that, even in its ground state, exhibits periodic motion. It is like a clock that keeps ticking forever at the absolute zero of temperature without any energy input. It does not violate the laws of thermodynamics because it is not doing work, it is not an energy source. It is simply in a state of persistent, structured change. The secret lies in a broken symmetry. Just as a regular crystal breaks spatial symmetry by arranging atoms in a repeating lattice that looks different if you shift it by certain amounts, a time crystal breaks time translation symmetry. Its ground state is not static, it oscillates with a rigid, unchangeable period. You cannot find a moment in time where the system looks the same, except at intervals of its own intrinsic rhythm. It is a perpetual dance frozen into the fabric of reality itself. The underlying field enabling this could be thought of as a time crystal field, a hidden pattern of correlations that locks the system into this eternal tick-tock. Visualize a ring of quantum particles like ions or artificial atoms linked together. In a normal ground state, they would sit still. In a time crystal phase, they perpetually flip their quantum states in a coordinated sequence, one after another around the ring, like a never-ending wave of dominoes falling and resetting in a perfect loop. This is not a machine, it is the natural, lowest energy configuration of the system. Experimental proof arrived in 2017, not in a material cooled to absolute zero, but in controlled quantum systems. Researchers used chains of ytterbium ions suspended by electromagnetic fields or disordered diamonds with dense nitrogen vacancies. They kicked these systems periodically with laser pulses, driving them into a non-equilibrium state. Astonishingly, the systems responded at a period different from the driving force. They established their own subharmonic rhythm. If the laser pulsed every t seconds, the time crystal would only return to its initial configuration every 2t or 3t seconds. This subharmonic response is the smoking gun, a signature of a discrete time crystal, a system locked into a rigid temporal order that resists external changes. The mind-bending implication is a form of perpetual motion that is allowed by quantum law. It is a structure in time as rigid as a diamond is in space. For fundamental physics, this is a revolution. It reveals entirely new phases of matter that exist out of equilibrium, phases defined not by spatial arrangement but by temporal order. The potential applications shimmer on the horizon, particularly for quantum computing. The protected, rhythmic states of a time crystal could serve as incredibly robust quantum memories, their coherence defended by the very temporal symmetry they break, making them resistant to the noise that plagues quantum bits. Could this temporal order be a feature of the vacuum itself, a faint, universal ticking woven into the quantum fields? It is a tantalizing speculation. Time crystals show us that the ground state of things may not be stillness, but rhythm, and that the universe's deepest silence might be filled with an infinite, invisible metronome, counting beats we are only beginning to hear. That eternal metronome of a time crystal hints at a universe with deep, repeating patterns. But what if that repetition is not just in time, but in space itself and across every conceivable size? This is the world of the conformal field, a hidden mathematical symmetry where the universe forgets how to measure itself. Conformal field theory describes systems that are scale invariant, meaning they look exactly the same no matter how much you zoom in or zoom out. There is no preferred ruler, no intrinsic yardstick to tell you if you are looking at the microscopic or the cosmic. The most familiar visual of this is a fractal. Imagine the intricate branching of a snowflake or the infinitely recursive twists of the Mandelbrot set. Zoom into a tiny section, and you find the same complex pattern repeating again and again, a universe in a grain of sand made literal. This is not just a pretty picture, it is a fundamental property that emerges in physical systems at their most critical point. Consider a simple magnet heating up. At most temperatures, it has a clear sense of scale. The magnetic domains have a typical size, but at the precise Curie temperature, the point where it loses its magnetism, something magical happens. The system becomes critical. Fluctuations occur at every possible length scale, from the distance between atoms to the size of the magnet itself. The magnet no longer knows if it is big or small. It becomes a fractal landscape of magnetic influence described perfectly by a conformal field theory. This scale invariance is the signature of a hidden conformal field governing the phase transition. In the quantum realm, certain field theories are believed to flow under renormalization to these perfect scale invariant points in their parameter space. At these fixed points, the theory becomes a conformal field theory, a kind of attractor in the space of all possible physics. But the true power of this idea explodes when we connect it to our earlier journey into the holographic principle. This connection is the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT, perhaps the most profound discovery in theoretical physics in the last 30 years. It proposes a breathtaking duality, a perfect dictionary between two seemingly different worlds. On one side, you have a conformal field theory. This is a quantum theory without gravity, living on the flat boundary of a higher dimensional space. It is scale invariant and has a fixed number of dimensions, say 3 spatial plus 1 time. On the other side, you have a theory of quantum gravity in an anti-de Sitter space, a negatively curved universe with 1 extra spatial dimension. The mind-bending claim of AD-S/CFT is that these two theories are completely equivalent. They are two different descriptions of the same reality. The scale-invariant quantum field theory on the boundary contains, in its complex quantum data, a full description of the gravitational physics happening in the bulk of the higher dimensional space. The conformal field is the master code. The size scale in the bulk gravitational theory, how deep you go into the extra dimension, is mapped directly to the energy scale in the boundary conformal theory. A high-energy event on the boundary corresponds to physics near the boundary of the bulk, while low-energy, infrared processes on the boundary describe the deep, interior regions of the gravitational space. In this framework, a black hole in the bulk is described by a hot, chaotic state of the quantum field theory on the boundary. The creation and evaporation of a black hole is just the thermalization and cooling of that quantum state. Even the fabric of spacetime and its smooth geometry in the bulk is not fundamental. It emerges from the intricate entanglement of the quantum degrees of freedom in the scale-invariant field theory on the edge. This means the conformal field, with its property of having no intrinsic scale, becomes the hidden architect of a universe that does have scale, curvature, and gravity. It is the ultimate demonstration that our dimensional reality, with its forces and geometry, could be a grand illusion projected from a simpler, scale-less quantum script written on the cosmic horizon. The universe may not have a favorite size because at its most fundamental level, it is written in a language that has forgotten what size even means. That scale-less code of a conformal field governs from the boundary, but what about the particles within? Do they have a true, definite existence? The dominant Copenhagen interpretation says no, not until observed. But a persistent alternative whispers yes, and it is all guided by a hidden hand. This is Bohmian mechanics, also called the de Broglie-Bohm pilot wave theory, and its central actor is the quantum potential field. In this view, the strange world of quantum mechanics is not about probabilities and collapses. It is about real particles with real trajectories, forever steered by a real, though hidden, wave. Imagine a surfer riding a powerful, complex ocean wave. The surfer is the particle, say an electron. It has a definite position at every moment, a real path through space. The wave it rides is the pilot wave, the quantum potential derived from the wave function. This wave does not push the particle like a Newtonian force. Instead, it informs it. It guides the surfer, telling it where to go next based on the entire shape of the wave around it. The wave contains information about the whole experimental setup, including any slits or barriers. If you send an electron toward a double-slit apparatus, its pilot wave passes through both slits, interferes with itself, and creates a complex interference pattern across the detection screen. The electron itself, riding this wave, is guided along a single, definite path that winds through one slit or the other. But because the guiding wave has interfered, the possible paths for the electron become concentrated in the bright bands of the pattern and avoid the dark bands. Run the experiment with thousands of electrons, each with its own definite but hidden trajectory, and their collective landing spots will paint the familiar interference fringes without any spooky collapse of probability. This is a completely deterministic theory. Given the initial position of the particle and the state of the pilot wave, its entire future path is determined. The randomness we observe is not fundamental, it simply comes from our ignorance of the particle's exact starting point within the wave. This solves the measurement problem neatly. There is no collapse because the wave function is always a real pilot wave and the particle is always somewhere specific. The cost, however, is non-locality of a particularly stark kind. The quantum potential field guiding the particle is sensitive to the entire environment instantaneously. In the famous EPR experiment, if two entangled particles are guided by a single, non-separable pilot wave, a measurement on one particle here instantly changes the guiding wave for its partner far away, altering its trajectory. This action at a distance is built into the theory's heart, fulfilling Einstein's reluctant prediction of spooky connections. Contrast this with the Copenhagen interpretation, which holds that particles do not have trajectories, only potentialities described by a wave function that collapses upon measurement into a definite state. In Copenhagen, the electron does not go through one slit or the other. It exists in a smear of probability until observed. Bohmian mechanics restores a classical sense of reality to particles, but at the price of accepting a ghostly, all-pervading field that orchestrates their dance from behind the scenes. Visually, picture a single glowing dot moving along a shimmering, luminous path. Surrounding it is a vast, ethereal landscape of rippling contours, the pilot wave, which shapes the path's every twist and turn. The dot never jumps, it flows, guided by an intelligence embedded in the wave itself. While not the mainstream view, Bohmian mechanics stands as a powerful reminder that our quantum story is not the only one possible. It offers a universe where things are definitively somewhere, forever navigating the invisible currents of a hidden quantum sea. The ghostly guidance of a pilot wave suggests particles are connected by an invisible field, but what if that connection is the very fabric of space? This is the staggering conjecture known as ER equals EPR, a proposal that two of Einstein's greatest puzzles are in fact the same thing, revealing a hidden field that stitches reality together from the inside out. On one side, we have EPR, named for Einstein, Podolsky, and Rosen, who in 1935 highlighted the spooky action at a distance of quantum entanglement. When two particles become entangled, measuring one instantly determines the state of the other, no matter how far apart they are. Einstein hated this, calling it a phantom influence that seemed to violate locality. On the other side, we have ER, the Einstein-Rosen bridge, proposed by Einstein and Nathan Rosen in 1935 as a possible, though unstable, solution to his equations. A wormhole, a shortcut through spacetime connecting two distant points. For decades, these were separate ideas, one from quantum mechanics, the other from general relativity. Then, in 2013, physicists Juan Maldaisner and Leonard Susskind made a breathtaking leap. They proposed that every pair of entangled particles is not just mysteriously linked, it is literally connected by a microscopic wormhole, an Einstein-Rosen bridge too tiny to traverse, but real in the geometry of spacetime. Entanglement does not happen across space, it creates the space between them. Imagine two particles as tiny, glowing spheres. In the old view, they are separate, with an invisible quantum thread stretched between them. In the ER equals EPR view, that thread is not a line across emptiness, it is a tunnel, a throbbing, submicroscopic wormhole that directly links their positions. The space you perceive between them is an illusion. They are geometrically joined at the hip through a hidden dimension. This implies a profound hidden field, a connectivity field, that weaves the very stage of spacetime out of a vast, dynamic web of quantum entanglements. Where there is a strong entanglement link, spacetime is tightly woven and continuous. Where entanglement is weak or absent, spacetime might fray or even tear. In this vision, the smooth, curved geometry of Einstein's universe is not fundamental. It is an emergent collective phenomenon, like the smooth surface of a pond emerging from the frantic interactions of countless water molecules. The connectivity field is the rulebook for how those entanglement links form and interact to create the illusion of distance and dimension. The implications for quantum gravity are revolutionary. It suggests that to quantize gravity, we should not be looking for a graviton particle, but rather understanding how the connectivity field organizes entanglement into geometry. This framework offers a stunning new perspective on the black hole information paradox. When a particle falls into a black hole, it becomes entangled with the hole's interior. According to ER equals EPR, that entanglement instantly spawns a microscopic wormhole linking the particle outside to the information inside. Over time, as the black hole evaporates via Hawking radiation, the outgoing radiation particles become entangled with the earlier radiation. This creates a vast, complex network of wormholes connecting all the Hawking particles, essentially weaving the interior information of the black hole into the fabric of spacetime outside. The information was never lost, it was just stored in the geometry of the connectivity field itself, in the labyrinth of wormholes linking everything that ever interacted. Visualize a black hole not as a simple pit, but as a dense, thorny ball of entanglement links with countless microscopic wormholes threading through it and branching out into the universe, a hidden architecture preserving every bit of data that fell in. This idea paints the cosmos as a single, quantum-connected entity. The space between stars, the vacuum between atoms, all of it is sustained by an unimaginably dense tapestry of entanglement governed by the connectivity field. We are not just separate objects in a void, we are nodes in a cosmic network, our very positions defined by the quantum threads that bind us, through wormholes too small to see, to everything else in existence. The distance to a star may be a journey across space, but at the deepest level, it is just a long path through an entangled web, a hidden geometry written in the language of connection. That cosmic web of entanglement hints at a universe striving toward connection, but could that striving have a final, conscious destination? Our final theory takes us to the ultimate edge of speculation, to a point where physics, cosmology, and theology blur into one. This is the omega point, a concept most rigorously argued by physicist Frank Tipler, proposing that the universe itself is evolving toward a final, all-knowing singularity. It is not merely an end, but a transcendent completion. The theory begins with a specific cosmic fate, the Big Crunch. If the universe contains enough mass to eventually halt and reverse its expansion, all matter and energy would collapse back together in a fiery convergence. In the final moments of this collapse, as the cosmos contracts toward a point of infinite density and temperature, the computational capacity of the universe would skyrocket. According to Tipler, an intelligent civilization or a network of civilizations merged into a single cosmic mind could use this ever-increasing energy to perform an infinite number of computations in the finite time before the final singularity. This process would allow this ultimate intelligence to simulate every possible conscious experience that could have ever existed, effectively resurrecting every being that ever lived in a perfect, emulated reality. It is a form of quantum immortality on a cosmic scale, where consciousness escapes material extinction by being uploaded into the final, infinite computation of the universe. The hidden field enabling this is not one of force, but of information and consciousness itself, a field that evolves and complexifies until it becomes coterminous with all of reality. Tipler even ties this to the cosmological constant, arguing that for the omega point to be possible, its value must be precisely tuned to allow for the eventual collapse, a staggering fine-tuning that gives the cosmos a teleological purpose. The visual is both terrifying and sublime, the entire cosmos, every galaxy and atom, hurtling together not toward darkness, but toward a point of infinite light and knowledge, a final flash where all questions are answered and all stories are retold. Scientifically, the omega point theory is considered fringe, as current evidence strongly favors an ever-accelerating expansion leading to a cold, dark end, not a big crunch. Yet, as a provocative synthesis, it compels a profound question. If the universe has hidden fields that govern matter, energy, and space, could there also be a hidden trajectory, a pull toward complexity and consciousness woven into the laws themselves? It is a theory that dares to see the cosmos not as a random accident, but as a story with an ending where nothing and no one is ever truly lost. From the chaotic foam of quantum spacetime to a conscious cosmos reaching its final thought, we have crossed an astonishing landscape of ideas. We began with the tangible, with the Higgs field giving mass to the world, and the inflattened field stretching the infant universe to its vast proportions. We wrestled with the dominant ghosts of our era, dark matter and dark energy, pondering whether they are substances like axions or chameleons, or a sign of gravity's hidden geometry like torsion or MOND. We ventured into the mind-bending architectures of string theory, where dilatant fields might change the constants of nature and Kalb-Rammond fields twist in unseen dimensions. We considered reality as a hologram projected from a conformal code and particles as surfers on a deterministic pilot wave. We dared to speculate on fields of collective memory, a planetary noosphere, and even a fundamental field of consciousness itself. Each theory, from the rigorously tested to the philosophically profound, represents a different thread in the same grand tapestry, a single, relentless human endeavor to peel back the veneer of the visible and discover what truly lies beneath. This is not merely science, it is the deepest story we have ever tried to tell about where we are and what we are made of. So, which of these hidden fields resonates most with you? Do you find the elegant mathematics of the Erfolgstein mechanism compelling, or does the tangible weirdness of time crystals capture your imagination? Share your favorite in the comments below and let us know which idea you believe will be the next to move from speculation to established truth. If this journey into the foundations of reality left you wondering, there are countless more mysteries waiting to be explored. Subscribe and join us as we continue to delve into the secrets of the cosmos, from the smallest particles to the farthest reaches of space. Remember, the universe is far stranger and more wonderful than it appears, and every hidden field we uncover is a step closer to understanding the magnificent hidden script of existence.